Okay, chapter 9. It says the reaction between zinc and a solution of copper 2 nitrate. So if we have zinc and copper 2 nitrate, let's start writing this chemical equation. So what is that chemical equation going to look like?
Zn
Zn
plus copper nitrate, which is CuNO3, and then is that going to be in, that's going to be in parentheses with the 2.
Okay, NO3 in parentheses. And you said a 2 at the end of it? Okay, what state is zinc in? What is the state of zinc?
Is it a solid?
It's a solid. And copper 2?
Aqueous.
Aqueous. And we're going to make
Zn and then NO3 plus Cu.
Okay, so I'm going to give you a little hint here. Anytime that you have any transitional metal, except for like aluminum is a post-transitional metal, but any transitional metal except for silver, when you're doing a single replacement, it's usually going to be a +2 charge on that metal. So zinc is going to have a +2 charge associated with it. So how would I account for that with my nitrates?
Okay. It would be NO3 parentheses 2.
That's right. And that's AQ. Plus Cu. Okay. So is it balanced?
Yes.
Okay. Okay, so this would be our conventional equation. So if we wanted our total ionic equation, what would that look like?
Zn.
Okay.
And you leave that alone because it's a solid.
Okay.
And then you would have Cu 2 plus aqueous, and then plus NO3 2 minus.
Cu, let me catch up with you. And you said 2 plus aqueous. Plus, you said NO.
NO3.
NO3. Remember I told you it's kind of like Velcro, right? So if it's like Velcro and the Velcro is holding it together, so like the copper is acting like the Velcro, and then I have like the little balls that has the fuzz on it, and I'm throwing those balls. So I have 2 nitrates on there. But if I don't have the Velcro, isn't it going to cause everything to be separate?
So are they going to be separated?
So they're going to be coefficients.
Oh,
that's
yeah.
right. Okay. So, and that's gonna make
Zn. Would that be a solid or an aqueous?
aqueous, right? Because it's all together. It's a
Oh, yeah.
so it's aqueous, so it'd be Zn what?
Plus 2.
2 plus. Okay. And that's aqueous.
Plus 2NO3 minus. And then plus Cu2 plus.
Aqueous. And plus copper metal.
Solid.
Yep. Okay. So who are our spectators?
2NO3 minus.
Okay, so then our net ionic equation is going to be
Zn solid plus copper.
the copper ion, copper 2 ion.
Okay, so 2 plus aqueous.
Okay.
And then the line. And then Zn2 plus aqueous plus Cus.
Plus Cu solid, right? Piece of cake?
Yes.
Okay. Any questions? Great having one person that I'm talking to. It makes it real easy. Okay. Okay, let me clear. Okay, so when we're talking about those single replacement reactions, so this is a hierarchy. You guys know what I mean by a hierarchy? Anyone? Miss Ma. Priscilla, are you there? Leanne, are you there?
Yes.
Okay, Leanne, help me out here. So when I say a hierarchy, what do I mean?
A hierarchy?
Yes. Do I
A
say
hierarchy is like the order, like the
like,
order that it goes in.
okay, so there, it's like an order, yes. So if something is a hierarchy, basically that means that things are in a certain type of order, right? So things are higher than others in that type of order. So when we're talking about single replacement reactions, we have a hierarchy with the different types of metals. So this here represents a hierarchy of the activity series. So the higher it is on this list, that means it can replace the things that are below it under these circumstances, okay? So for instance, if I have lithium metal, it can replace everything that is below it if it's in a liquid water, steam, or an acid, or any type of solution, okay? So lithium metal can replace any other metal that's below it in the series. So let me give you an example. Let's say I had calcium nitrate. We know that calcium nitrate is Ca, NO3, two. We need two of those. Okay, so if I have lithium metal, it's going to be able to replace calcium because calcium is lower than it on the activity series. So I would get a reaction Of course, I'd have to balance it out. Okay, questions? Okay, now, if I have a metal that is lower than another metal, let's say we have calcium here, and I have barium nitrate, because calcium is lower than barium, it won't be able to replace it. So we won't get a reaction. So NR stands for no reaction. Okay, do you guys understand that?
Yes.
Okay, so if you guys look in your packet with your periodic table, you have the hierarchy on there. Okay, so you should be able to sit there and tell me if a reaction is going to occur or if a reaction isn't going to occur, just like I just did in this case. Okay, so do you want to give this a test run, or do you got it? You don't need me to go over it.
Let's go over it.
Okay, so let's go over it. So let's say we have magnesium metal reacting with silver nitrate. Silver 1 nitrate. Am I going to get a reaction? Or is it going to be no reaction? And if I am going to get a reaction, what are going to be my products?
MgNO3. Wait, it would be in parentheses the nitrate.
That's right.
And 2.
That's right.
Plus Ag.
Plus Ag. Okay, piece of cake.
Yeah.
Okay, let's try one more. What about Okay, so I'm going to give you a little bit of a hint. It basically tells us if it's going to be able to happen. So magnesium will be able to replace hydrogen if it's steam or an acid. Barium will be able to replace hydrogen if it's from liquid water, steam, or an acid. Iron will be able to replace hydrogen if it's from an acid. So, will iron be able to replace water?
No.
No. So then it would be no reaction. Okay, do you guys get that?
Yeah.
Okay. Anybody not get that? Okay. Let's move forward then. Okay, so we've talked about combustion reactions already. You guys are very familiar with them. They're often also called oxidation reduction reactions when we're talking about organic compounds. So we know that with a combustion reaction, we always are going to end up with carbon dioxide and water. Okay? So we should be able to know that we're going to get that type of equation, right? So here's the question. Write the equation for a complete burning of ethane. So if I'm going to write the chemical equation for the complete burning of ethane, what am I going to do? Jose, are you there? Yes, no, maybe? How about, let's see, we have Fatima, are you there? Okay, we'll go down the list. Alicio, are you there? Okay, Haley, are you there?
Yeah.
Okay, Haley, represent. So what do we need to do? If we have complete burning of ethane, so how are we going to start writing this chemical equation?
You're gonna write down what you're given.
Okay, so we're given C2H6, and we know that that's a gas.
Mm-hmm.
Okay, so what is required for organic material to burn?
Oxygen.
Oxygen. So what is the chemical formula for oxygen?
O2.
O2. And we know that that's a gas.
Mm-hmm.
So what are we going to make when we burn something? We're always going to get the same two products. What are they?
C2O2.
C2O2? Okay, let's think about this. So you guys do this all the time, right? So you guys basically do a combustion reaction all the time when we eat. So if you eat a whole bunch of sugar, right? You eat food, what do? You breathe in oxygen,
Mm-hmm.
right? You breathe in oxygen, you eat, and then what do you breathe out?
Carbon dioxide.
Okay, what is the chemical formula for carbon dioxide? Carbon dioxide.
Oh yeah. C. And then O2.
O2, that's right. And we know that that's a gas.
Mm-hmm.
Okay. Now, what is the major, what makes your tinkle, your pee, water? I mean, what makes your tinkle liquid?
Water.
Water, okay? So you also produce water. So anytime that you're breaking down a hydrocarbon, you're gonna get water and carbon dioxide. So have you guys ever been to a bonfire? Bonfire? Any of you guys have ever been to a bonfire?
Yes.
Okay, so now you know a bonfire is not a barn burning down, right? You guys know that, right? You guys didn't burn down a barn, did you?
No.
Good, okay, good. Okay, so now if you go to a bonfire and you sit there, you throw all that wood on there. So you're gonna get a lot of charcoal and stuff like that. So you're gonna get, some of it is gonna be charcoal, but a lot of it is gonna be gases that are gonna be coming off. Don't you see some of those gases, that smoke coming out? Some of that is just that carbon dioxide, right? Actually, a lot of it is that carbon dioxide. And another part of it is actually steam, because we know that we have steam coming off of it as well. So we have water in its gaseous form. Okay, now is this balanced?
No.
Okay, what do I need to do to balance it, Yesenia?
You need to put a 7 in front of the O2
Okay, 7 in front of the O2.
on the reactant side. Yeah.
Okay,
And then on the product side, you put a 2 in front of the CO2.
put a 2 in front of the CO2.
Yeah.
Okay,
And then a 3 in front of the H2O.
and the 3 in front of the H2O. Okay, so then that will give me, let's see, that's 2 times, so that would be what? Oxygens, that's 4, that's 7 oxygens. That's 6 hydrogens, and that's 2 carbons. And so over here I have 2, and I have 14.
It would be a fraction.
It should be 7/2, right?
Yeah, 7/2.
Okay,
then
so it should be 7/2. So then I have to multiply everything by 2, right? So
Yeah.
then this guy gets multiplied by 2. 7/2 become 7. This guy becomes 4. And this guy becomes 6. Is that right? I'm making stuff up.
Yeah.
Yeah, so then that would give me 4 carbons, 12 hydrogens, and 14 oxygens. So everything balances out. Okay, pretty simple.
Yes.
So take home message, anytime that you have a hydrocarbon or an organic molecule burning, we know that that's always going to provide oxygen because the air is going to provide the oxygen for us. Okay, so if we want to stop a fire, the best way of stopping a fire of an organic piece of material is to do what?
Add water.
Oxygen.
To remove the oxygen, to cover it so that you can't get any more oxygen, right? So if you can cover it so you can get no more oxygen, it's the best way of doing it, right? Okay. So have you guys been cooking and then the stove catches on fire? Does that ever happen to you?
No.
No? Okay, you guys are good cooks. I'm gonna say probably once every, I'm gonna be nice here. Once every month, I probably will catch a fire in the kitchen because I forget I'm cooking, right? And so especially if I'm using grease, I have a grease fire. the best way of putting out a grease fire is taking a pan that doesn't have a little hole or anything in there so that oxygen can get in there and covering it completely. The fire will go out. Have you guys ever played with the candles? You guys bought candles from like Bath and Body Works.
And then
Yeah.
Okay,
Yeah.
so all of those candles come with lids. So next time, instead of putting out the candle with your hand or something like that, just put the lid on top of it and see what happens.
Yeah, the fire goes out
The fire goes out. Why?
because there's no oxygen.
Because there's no oxygen. That is correct. Pretty simple, right?
Yeah.
Okay. So we've talked about double replacement reactions before, right? So, but usually we haven't talked about them in the context of a precipitant, or we have, but not really. Okay, so what I mean by that, a precipitant is that when you get two parts that come together to make a solid, and the solid stays together, it can't be separated by water, it precipitates out. So do you guys remember when you guys were sitting there doing it? I think you guys did silver nitrate and sodium chloride, right? And so when silver chloride came together, it formed a solid, and you started getting it would be like a black color, I remember, or a gray color. I can't remember exactly. Either a gray color or a black color, and it started precipitating out of the reaction. Do you guys remember that?
Yeah.
Yeah. Okay. So that's an example of a double replacement that give us a precipitant. Okay. Now, the way that we determine whether or not a precipitant is going to form is if things are soluble or insoluble. One way of doing it is by using the solubility table. This here is a solubility table. So if we put two things together, let's say we have aluminum acetate. Aluminum acetate, if it comes together, it's going to form a solid. So anything that's in the orange color, it'll say slightly soluble, insoluble, nearly insoluble. Anything in the orange color is going to form a precipitant. Anything that's in the green color is going to stay dissolved in solution. Okay, so if I have copper 2 acetate, it's going to dissolve in solution. If I have cobalt 2 acetate, it's going to dissolve in solution. But if I have cobalt 2 carbonate, it's going to form a precipitant. Do you guys understand? Are you with me?
Yeah.
Okay, so let me give you an example. So let's say we have cobalt 2 acetate, which is C2H3O2, and it takes two of those because we know that acetate, if we look on our polyatomic ion table, has a negative charge. So we'll need 2 acetates to balance out the +2 charge on the cobalt. Okay, we know that when we put in solution into an aqueous solution, is going to completely dissolve. So we're going to put AQ next to it. And if that reacts with ammonium carbonate, actually, let's do sodium carbonate. We'll do sodium carbonate. AQ. So we know that anything that's group 1 metal with anything is in aqueous solution is going to dissolve. So if it's with the chloride, it's going to dissolve. If it's with carbonate, it's going to dissolve. So any group 1 metal with any other thing, it's going to be able to dissolve. Okay. So if I do a double replacement reaction, I'll have cobalt and what?
CO3.
Cobalt and CO3 and carbonate. So cobalt and CO3 is pink. So that means it's going to form a solid. So we're going to put an S there. Where sodium acetate, let's go look on the other slide. Hopefully it's there. So we have sodium acetate. It tells us that it's soluble. So that means that it's going to be aqueous. Okay, do you guys see how it works?
Yeah.
Okay. Okay. See, if you don't want to use this table, what you guys can do, you can also just memorize this. So this lets us know what is going to be soluble, what's going to be insoluble. So almost all salts of sodium, potassium, and ammonium are soluble. Salts of nitrates, nitrites, chlorates, perchlorates, and acetates are almost always soluble. Almost all salts of chloride, bromide, and iodide are almost always soluble. And then these are some of the exceptions. So for acetates, aluminum acetate is insoluble. Silver acetate is insoluble. Silver nitrate is insoluble. In terms of the chlorides, so chlorides with silver, with mercury 1 ion, and with lead 2. And then fluorines, all of these guys are insoluble with fluorine when they come together. Okay, so do you guys understand how this works too? And this should also be in your packet. Okay, great. So let's see how well you guys understand. A solution of lead 2 nitrate and sodium bromide are combined. Write the net ionic equation for any precipitation reaction that may occur. So how would I write that?
PB.
Okay.
And then
PB.
NO3 in parentheses, Ne2.
Okay.
Plus Na Br2.
Is it Br2? Where's sodium located at?
Yeah, never mind. It's right like that.
Okay. Okay. Both of these are aqueous since it says it's solutions. Okay, so then what else? What are we going to make?
PB and then BR2
That's right.
plus NaNO3.
Okay. So let's go take a look to see which one is going to form a solid and which one isn't. So if we go back to that table. Okay, so we have lead to bromide. So lead to bromide. Okay, you guys see it on that table? Lead
It's
2 and bromide.
soluble.
Slightly soluble. So what does that mean? Do I put an S by it or do I put an AQ by it?
S.
An S, that's right. It basically, anything that's in that pink is going to be a solid. Okay, what about sodium nitrate?
It's going to be an aqueous.
That's right, AQ. Okay, piece of cake. Are we done anyway? Are we balanced?
No.
Okay, so what do we need to do to balance it?
You add a 2 to the NABR.
So I need a 2 to the NABR. Okay,
And a 2 in the lead nitrate. And yeah, they're 2.
you mean sodium nitrate. Yep. Okay, is it balanced now? Yes,
Yeah.
no, maybe? Okay. So I'm assuming that's a yes. So it is balanced. Okay, so now if I was writing the total ionic equation, I think we did this one pretty much already, right? So it's Br. What would be the charge on our Br?
That would be 2 on the PB.
I mean, sorry, Br. I mean, PB at 2 plus, right?
Yeah, and that's aqueous
Aqueous.
plus 2NO3 negative
Okay.
plus 2Na plus aqueous
Plus 2Na plus
2Br negative.
Br negative. Aqueous. Okay. And on the product side,
PB2 plus solid
okay.
plus
PB2 plus, well,
yeah.
what is the rule about solids, liquids, and gases?
Oh wait, you leave them alone.
They stay the same.
That's right, they stay the same. That's right. So we're going to leave this guy alone. Okay. Plus
2Na plus aqueous plus 2NO3 negative aqueous.
Okay. Who are our spectators?
Your nitrate and sodium.
Okay. Okay. So then my net ionic equation is going to be
Pb 2 plus aqueous plus 2Br negative aqueous, and then your yield sign PbBr2 solid.
okay. Oops. PB. Okay. Questions, concerns, Cash? Too late? Okay. So when we talk about acids, acids are also a special form of a double replacement reaction. So in that case, we have hydrochloric acid and sodium hydroxide. So what is the chemical formula for hydrochloric acid? Hydrochloric acid. Anyone? Mariana? Margarita? Steven?
Is it HCl?
HCl, that's right. HCl. And we know it's AQ. Plus, what about sodium hydroxide?
Na OH.
And it says a solution of that.
Aqueous.
Okay. So if it's a double replacement reaction, and we've kind of talked about an acid. So if we have a strong acid and a strong base that come together, we're going to form what and what? So I have this guy is going to hook up with this guy. It's going to form what?
H2O.
H2O. So water, solid, liquid, gas, or aqueous.
And then the other one's a salt, right?
And a salt. Yep, that's right. So NaCl. Happens to be salt perfectly. Sorry about that. I keep writing my A on top of my N. NaCl. So is that going to be solid, liquid, gas, or aqueous? Let's look at that table. Sodium chloride. Is that solid, liquid, gas, or aqueous?
Aqueous.
That's right. Okay. And water, is that going to be solid, liquid, gas, or aqueous?
Liquid.
That's right. Okay. Is it balanced? Yes. No? Maybe?
Yes.
It is balanced. Okay, so we're done. Oh, we're done with the first part. Okay, so now the next part is if I want to try to get the net ionic equation.
H plus aqueous plus Cl negative aqueous plus Na plus aqueous plus OH negative aqueous, and then your yield sign, and then
Okay. Keep going, I'll catch up with you.
H2 plus. Wait, would the H2O be together or separated?
It's together because it's covalently bonded. So
then it's H2O
and it's a liquid, right? So what's the rule about liquid gases and solids?
Q alone, they stay the same.
That's right.
So then it would be plus Na plus aqueous plus Cl negative aqueous.
Okay, our spectators.
Na plus aqueous and Cl minus aqueous.
Oops. Yeah, there we go. So we get our net ionic equation is just going to be H AQ plus OH minus AQ and that's going to yield H2O. Okay, and that's liquid. Questions, concerns? Okay, moving forward. Okay, sometimes we'll end up getting a reaction that is unstable. So like for instance, when we form, let's say, if it's forming independently, carbonic acid is unstable. So if we're forming it from two independent sources, so we're getting the H from one source and the carbonate or carbonate ion from another source, when it comes together, it forms what we call carbonic acid. Carbonic acid almost instantaneously breaks down to carbon dioxide, gas, and liquid water. Same thing with sulfuric acid. If we're forming it independently, right, from a source of H plus and an SO3 minus, 2 minus, then when they come together, it's going to form an unstable form of sulfuric acid. Well, that's actually going to be broken down almost instantaneously to sulfur dioxide and water. And the same thing happens with ammonium hydroxide. So as soon as we get ammonium hydroxide together, it forms an unstable version of ammonium hydroxide, and it breaks down to ammonia and water. So it stinks. So that's the reason why we have to put it in the incubator, in the hood, because of that smell. Okay, so if we have sodium carbonate and hydrochloric acid that are going to be coming together, so what is the chemical formula for sodium carbonate?
NaCO3.
NaCO3. And that's going to be aqueous since it's a solution. And that's going to be reacting with hydrochloric acid. Chemical formula for hydrochloric acid again?
HCl.
Okay. And that's going to yield. So it's a special double replacement reaction. This guy's going to hook up with who?
Na.
Na.
So it would be NaCl.
Okay.
Plus HCO3.
Are you sure just HCO3?
H2.
Carbonic acid. Oh, this is a mistake here. This should be a 2. Okay.
So H2CO3.
H2CO3. Okay, so we know that this guy's unstable because we just talked about it. So if I have a HCO3, what is it going to end up making?
A solid.
No, we just talked about it. If I get my independent source of the hydrogen and independent source of my carbonate and it's coming together, it's going to do what? Let's go back and look. Do you guys see that? So carbonic acid, is that what I got here? H2CO3.
Yeah.
Okay, so it's going to break down immediately to
CO2 G plus H2O liquid.
plus water, right? Okay. Are you guys clear on that?
Yeah.
Okay. So let's bring this back up. So if we're writing our conventional equation, our final conventional equation, let me fix this up. So we'll end up with Na. Let me put it in a different color. Put it in blue. So Na to C. CH2O3AQ plus HCl AQ, and that's going to yield NaCl AQ plus CO2 gas plus H2O liquid. Okay, so if we did the total ionic equation,
Na, well, it's 2Na
okay, so
plus
2Na plus
aqueous plus
AQ,
CO3 2 negative aqueous plus 2H plus, oh, and it's just H plus
okay,
aqueous plus Cl negative aqueous, and then your yield sign, and then
okay.
it's,
Oh, by the way, is this balanced? Shouldn't there be a 2 here?
yeah, it's not balanced.
Yeah, let's put a 2 here, and that messes everything else up. Okay, so now we can fix this. So it'll be 2 H plus
Yeah, aqueous
aqueous
plus 2Cl negative aqueous, and then your yield sign, and then 2Na plus aqueous plus 2Cl negative aqueous plus CO2 gas plus H2O liquid.
Okay, good job. Okay, spectators,
2Na plus and 2Cl negative.
so the net equation I'm going to put up top here is going to be and that's going to yield CO2, gas, and water. Okay, questions, concerns, Cash, Kool-Aid. Okay, good. I'm going to erase. And So we're going to skip this one. Okay, so there are cases when we have a double replacement reaction and there are going to be no products, right? So that happens when everything totally dissociates. So we have sodium chloride, NaCl, plus potassium nitrate, which is KNO3. What are going to be the products from this reaction normally in a conventional chemical equation?
It would be Na with NO3,
Na with NO3
K, and Cl.
plus KCl. Okay, so let's go to that table. Maybe. Okay, there we go. So we need potassium. So potassium is soluble for everything, and sodium is soluble for everything. Right? So we know that it's going to be aqueous, right? Because if we have potassium chloride, so then there's going to be an AQ here. And we have sodium nitrate is also going to be AQ. So if we did the total ionic equation, we're going to end up with Na plus Cl minus AQ AQ plus K plus AQ plus NO3 minus AQ that's going to yield Na plus nitrate ion. Both of those are AQ. Plus K plus Cl minus AQ. Okay, so who are the spectators here?
All of them?
All of them. Okay, so anytime that you have everything that's a spectator, that basically means that there is not going to be a reaction that's going to occur. Everything is just going to stay in solution. So here you would just write in no reaction. So you'd go NR. Okay, piece of cake?
Yes.
Okay, good. Okay, I think we've covered everything. So this is all chapter 9. I know it's a lot of information, but it's pretty straightforward, right? If it's an ionic compound, it can break down under an aqueous solution. And then if it's reforming, you could sit there and determine whether or not which two products are coming together and whether or not they're going to be soluble or insoluble, right? By using that table. You can figure out the hierarchy of things, in the case of a single replacement reaction, right? So if we have this chemical equation, this is the chemical equation for ammonia reacting with oxygen. It's going to form nitrogen monoxide and water. Okay, so this is a balanced chemical equation. Wouldn't you guys agree? Yes or no? Okay, so it is balanced. Okay, so the thing that are balanced chemical equations, those coefficients will let us know the mole to mole ratio. Like for instance, for every 4 moles of ammonia, we're going to need 5 moles of oxygen gas so that we can get this reaction to happen. And for every 4 moles of ammonia, I can make 4 moles of nitrogen monoxide. So we're able to sit there and set up what we call a mole to mole ratio. And we can use it in any order. We could use it where we have the moles of oxygen on top and the moles of ammonia on bottom. We can use it where we have ammonia on top, oxygen on the bottom. So it can go either way. Okay, are you guys with me so far? Because we can do this, this allows us to sit there and go from moles of one to figure out how much of moles of the other I'm going to need, right? So kind of like when we were talking about making that cake, right? Let's see. So if I have 3.20 moles of ammonia react according to the equation, the past equation, how many moles of water will be produced? So where am I going to start at?
You would do the equation, right?
Okay, so we're going to use our equation, going to go back. Okay, here's our equation right here. Okay, here's our chemical equation. So what's my given? What was my given in that problem? I believe it says 3.20 moles of ammonia. Is that right?
Yes.
Okay. And I want to find what? What am I looking for? Was it moles of water?
Yeah.
Oops. Okay, so if I want to get to moles of water, which one of these ratios am I going to use? I'm starting with moles of ammonia, and I want to get to moles of water. What is going to be my ratio?
The
Based
one on
upon,
your right hand side, the 6 mole
Okay.
H2O.
okay, so I have 6 moles of H2O. I want to have that on the top because that's what I want to end up with is moles of H2O. And then what is going to be on the bottom?
The 4 mole NH3.
That's right. That is correct. So I'm going to have 4 moles of NH3. Okay. Moles of NH3 are going to cancel out. And then I should just be left with moles of water. If I do this, I should end up with what?
.8.
Okay. How many sig figs should I have?
3.
3. That's right. Okay, so I end up with 4.8 moles of water. Simple.
Yes.
Okay, so this is called stoichiometry, this process of using that mole to mole ratio, right? So if I know what I'm given, how much I'm starting out with, I can figure out how much I can make of the other, right? Or how much I need to react with things. Okay. Okay, so here, if I'm given my reactant, I can figure out how much product I can make, right? So it's not a black box. If we have the chemical equation, we can figure out how much we have. Okay, so it's that process of using that mole to mole ratio. Okay, so how many moles of oxygen are required to burn 2.40 moles of ethane? First thing I'm going to do is to do what?
Write your equation.
Write my chemical equation. Okay, so I have ethane, C2H6 plus oxygen. Oxygen, what is the chemical formula for oxygen?
O2.
O2. And that's going to yield
CO2 plus H2O.
so we balanced this the last time, if I remember correctly. We had a 7 here, we had a 2 here, we had 4 here, and we had a 6 here. Okay, so is it balanced?
Yes.
Yep, I forgot my G's. Thank you, Alyssa. I've gotten that wrong on my test. Okay, so if I have 2.4 moles of ethane, 2.40 moles of ethane, how many moles of oxygen are going to need it to react with it? So how would I figure that out? Somebody said X. So what's going to go on the bottom and what's going to go on top?
On the bottom is the C2H6, and on the top would be your oxygen.
So I'm going to have moles of C2H6. So what is the moles of C2H6? How many do I have in my chemical reaction?
2.
2, or should I say my coefficient that I'm using. So it's 2 moles of C2H6. And on top, it's going to be oxygen. What is the?
7.
Okay. So what do you guys get?
8.4. And so it would be 8.40
8.40. That is correct.
mole O2.
Okay. Simple, not too hard. Questions? Okay, good. So if I'm given my mass, I know that if I'm given mass, if I'm going to use my chemical equation to try to figure out something that is being produced or something that I need to react with, I know I always have to change it to moles. So if given mass, I need to convert to moles, and then I can use my mole to mole ratio to get the moles of what I'm given to the moles of what I want. And then if I want the mass of what I want, then I can convert back to mass, okay, of what I want. Okay, and this is just showing you that process. So if we're going from mass to the mass of something that we want, mass of what given to the mass of something that we want, we have to go from mass to moles, use the mole to mole ratio, and then go back to mass, okay? We are gonna stop right here. We'll pick this up. Our last lecture, unfortunately, will be tomorrow. So I will go over this tomorrow. So that means I'm gonna give you guys until Sunday to complete your final. Actually, I'll give it to you Monday. Monday to complete your final, okay? So did you guys hear that? Do you want me to repeat it one more time?
So there's gonna be a fourth final? A fourth exam, I mean?
Yes, there's gonna be a fourth exam, which is your final. So you have the third exam, which has to be completed, technically be completed today. I will give you guys this third exam. I will give you guys till Friday to complete that. I will give you till Monday to complete your final. This third exam does not include any of the things that we've covered today or that we covered yesterday or the day before. Your fourth exam will include all of that, everything that we're gonna be covering up until tomorrow. Does that make sense?
Yes, thank you.
Okay, now if you're anxious, you can take the exam on, the final on Friday. You're more than welcome to do it. Your final is open, your practice final is open. You should be able to have access to that if you want access to that. Okay?